Alright, so a question to consider. Why is the chemical equation on the left correct, whereas the chemical equation on the right-hand side is incorrect? So let's start by looking at the differences. Well, on the left-hand side one, we've got a 2 coefficient in front of the hydrogen molecule and in front of the water molecule, whereas for the right-hand side, all the coefficients are 1. So basically, this goes back to this idea of balancing chemical equations, where you have to have the same number of each atom type, in this case hydrogen and oxygen, on the reactant and product side. And that, if we worked out the number of each atom type on each side for both equations here, we would see that in the blue, this one is balanced because there's the same number of hydrogen atoms and oxygen atoms on the reactant side as there is on the product side, whereas in the red version of the equation, the chemical equation is actually unbalanced because there's different numbers of hydrogen and oxygen atoms on the reactant and product side. So essentially, for what we represent in our chemical equations to be real, in terms of being an actual representation of a chemical reaction, we need to make sure that it is balanced. So what this means is, for this equation, we would actually need 2 molecules of our H2 to react with 1 molecule of oxygen to create the product, which in this case is 2 molecules of water. You can't have 1 molecule of hydrogen and 1 molecule of oxygen creating 1 molecule of water because the atom types don't match up. In this case, there's more oxygen atoms on the left-hand side than there are on the right-hand side. 2 here and 1 here, which tells you that the equation is not balanced. So the next thing we're going to have a look at is how to go about balancing chemical equations. So you'll have some of these questions in your tutorial and also some ones to work through in the actual session to practice balancing the chemical equation. So usually you'll be given a chemical equation without any coefficients, like we saw here, and your job will be to basically add the coefficients in front of some of the molecules to make sure you've got an equal number of atom types on the reactant and product side. So there's a method we can use to balance chemical equations. The first step is simply to determine whether the chemical equation is balanced or not. And you can do this by counting the number of each atom type on each side. So how many oxygen and hydrogens are on the reactant side and how many oxygen and hydrogens are on the product side. So once you've established that the chemical equation is unbalanced, then we move on to step 2, where you try and change one or more of the coefficients to balance the chemical equation. Step 3 is essentially very similar to step 1. Essentially, you're just checking whether what you changed in step 2 by changing the coefficients was actually enough to balance the chemical equation. So the majority of what you're doing in balancing chemical equations is just counting the number of each atom type on the reactant and product side. And if it's not balanced, then you have to keep trying to change the coefficients until it does. There's a little bit of trial and error with this, and you may not get it right on the first attempt, but you can keep trying. So let's have a look at how this works. So to work out the number of elements atoms present in a molecule, we need to multiply the coefficient by the subscript of each atom. So we're going to use this method to work out the number of each atom type on the reactant and product side. So let's review how to do this. So for example, for the molecule Fe2O3, we've got a coefficient of 2 in front of it, which tells us that we've got 2 lots of everything that comes after that coefficient of 2. So we multiply each subscript for the atom type by the coefficient to get the number of atoms. So for the number of Fe atoms in 2 of these molecules, we'll do 2 times 2. So the coefficient of 2 is times by the subscript of 2, which tells us that there's going to be 4 Fe atoms represented there. Do the same thing for oxygen, times the coefficient of 2 by the subscript of oxygen, which is 3. So 2 times 3 is 6, which gives us 6 oxygen atoms. So here we have a example of a balanced chemical equation involving the molecule we see above here. So you can see on the product side we've got that 2Fe2O3, which is what we were looking at above here. So to create our two molecules of Fe2O3, we actually need 4 ions and 3 oxygen molecules. However, it would be incorrect to double all the coefficients, meaning you'd have 8 Fe's, 6 O2s, and 4 Fe2O3. So there's a rule when you're writing these chemical equations that you have to have the lowest possible coefficients. So essentially you can get from what we have here, what I'm saying is incorrect, by halving all of the coefficients. So if we halve 4, we get 2, halve 6, we get 3, halve 8, you get 4. So essentially, if your numbers are too large, just halve everything, and that will be the correct representation. Okay, so we're going to practice step 1 now for the chemical equation we see here to determine if the equation is balanced. So these tables that I've got in the slides are quite handy. So it's basically just working out what each type of atom is on the reactant side and the product side, and then counting the number of those atoms. So on both sides of the chemical equation, we've got iron atoms, Fe, and oxygen atoms. So you can see that inputted into the table here. So the next thing to do is to count the number of each type of atom present. So for Fe, there's no subscript, so that means we're going to have just one atom there. For O2, we've got a subscript of 2 after the oxygen. So how many oxygens would there be then? So we've got 2 oxygen atoms in that one molecule, so that becomes 2. And within our Fe2O3 compound, we need to look at the subscript that comes after each atom type to work out how many atoms of that type there are. So for Fe2, there's going to be 2 Fe atoms, and for O3, there's going to be 3 oxygen atoms. So that corresponds to the answers here that are in the slide. So you can see here that the chemical equation is not balanced. Why isn't it balanced? Because the number of Fe atoms is different on the reactant and product side, and so is the number of oxygen atoms on the reactant and product side. So essentially the chemical equation is unbalanced, so it's not a proper representation of the chemical reaction. So now that we've established that it's not balanced by doing step 1, we move on to step 2. So we've established that there's different numbers of each atom type there. So step 2 is balancing the chemical equation, and we can do this by trying to add different coefficients in front of the molecules. Basically what you're doing when you're doing this is you're saying there's more than one of the molecules present. So for example, if I put a 2 in front of O2, that's saying that there's now 2 lots of our oxygen molecule. Or if I put a coefficient of 3 in front of the Fe atom, then it's telling you that there's actually 3 lots of that one Fe atom. So essentially, you're trying to get what's on the reactant side to match what's on the product side. So there's a little bit of trial and error here, but you can use educated guesses by looking at what's on each side of the equation. So you can see that there's 2 Fe atoms on the product side, so we need to have 2 Fe atoms on the reactant side. So how can we turn our 1 Fe atom on this side into 2 separate Fe atoms? We can put a 2 in front of our Fe there. So that is telling us that now we've got a new coefficient, 2 lots of our single Fe atoms. Remember, we can't put the 2 down here because that would be a subscript, and that would be changing what the component actually is. So we're only ever adding or changing coefficients. You can't change subscripts. Okay? So always putting numbers in front of the atoms or molecules, not introducing different subscripts. So we've got a 2 out in front of our Fe here, and if we look at our oxygens, there's 3 of them on this side and 2 of them on this side. So basically, we need to find an intermediary between 3 and 2. So to do this, you can basically just times 3 and 2 together, which gives you 6. Because 6 is a number that both 3 and 2 can be divided by. So essentially, once you've worked out what that number is that they can both be divided by timesing the two together, then you just need to find a way of actually getting to that number of 6 for each of the oxygens here. So how can we turn O2 into 6 oxygen atoms? Well, we can change the coefficient here to be 3, because 3 times 2 oxygen atoms is 6. What about for our O3 here? How many lots of our O3 will we need to get to 6? So if we have 2 lots of our O3, then that will equal 6. But look what we've done here. We can't just put the 2 in front of the oxygen. We have to put the 2 in front of this whole molecule. So by getting 2 lots of the O3, we've also increased the amount of our Fe2. So that tells us that we've now got 2 lots of Fe2. So 2 times 2 is 4. So that now means we actually need more Fe atoms on the left-hand side here. So how can we get 4 Fe atoms on the reactant side here? Well, we don't need 2 anymore here. We need a new coefficient of 4. So this is what I mean by trial and error. Initially, it looked like there was only 2 atoms needed for Fe on the left-hand side, but by working through to try and get the same number of oxygens on the reactant and product side, it actually meant that we needed more Fe atoms on the reactant side. So this is the trial and error portion of the balancing of the equation. You can actually check whether you've balanced it at any different stage. So for example, after I'd put the 2 Fe, you could have checked it then by applying the method I showed you in step 1, or if you thought it was balanced after we added the 3 in front of the oxygen for the coefficient, you could have checked it. But if you check your equation and it's not balanced, then you have to keep trying to change the coefficient until it does become balanced. So now that I think I've balanced the equation, which it looks like I have because the numbers match there, the third step is to actually check whether it's balanced or not. So this is basically just a repeat of step 1, counting the number of each type of atoms on each side. So using this table again, we've got iron and oxygen atoms, and now let's work out how many there are for each one. So 4 lots of 1 Fe gives us 4 Fe atoms here, and then 3 lots of 2 oxygens here gives us 6 oxygens. The 2 in front of our Fe2O3 means we times the 2 Fe atoms by 2 and also the 3 oxygen atoms by 2. So 2 times 2 for the Fe gives us 4, and 2 times 3 for the oxygen gives us 6. So voila, we have 4 iron atoms on the reactant side, 4 iron atoms on the product side, and 6 oxygen atoms on each side as well. So we've actually been able to balance the equation. Okay, so this shows us that yes, the chemical equation is balanced. This is a real representation of how iron and oxygen would react together to create our Fe2O3 compound. Okay, so no matter what chemical equation you get, you can apply these 3 steps to try and balance the equation. So it's essentially, firstly, just working out whether it's balanced. If it's balanced, then you don't have to do anything else. You've shown that it's been balanced. But if it's not balanced, then we have to try and change the coefficients to make it so there's the same number of each atom type on the reactant and product side. When you think it's balanced, you can then check it by adding up the number of atoms on each side.